Good morning. So, in this lecture, we are going to talk about aseptic processing. Since this course is focused on emerging food processing technologies, I am not going to discuss some of the conventional pasteurization, sterilization methods like canning, things of that nature, but those technologies utilize traditional conduction, convection heat transfer, and as a result, it takes longer time to process the food. Where while the canned products are quite safe, it degrades the quality of the product. As a result, the food industry has been looking for a better way to preserve the product quality. The second thing is canning is a batch process. So, that means you probably have a limited number of samples you can process any given time, and a lot of times the food processing industry always look for what I call continuous methods of processing, so that you can be able to process them for a better quality, faster, and maybe much more economical. So, having some of these reasons, the aseptic processing has been looked at. Per se, aseptic processing is not a new technology. Even in 1960s, the concept of aseptic processing was developed and have been kind of tested, evaluated by many research groups. In the US, the Food and Drug Administration, which regulates and issue letter of no objection for novel processing technologies, require food processor to demonstrate the safety of the processed food using scientific methods. So, some of those required lot of scientific research and development. So, that took almost 1996 before the first aseptic processing for particles was approved in the US. So, in this presentation, we are going to go through some of the basics concepts behind aseptic processing, some of the equipment associated with that, and then what makes the food safe, how do you validate the process technology, and other related topics. So, when you are sterilizing food, that means you inactivate all the vegetative bacteria as well as spore formers. You kind of want to increase the temperature of the product instantaneously, so that you kill the bacteria and the spore forming bacteria without damaging the nutrients. If you remember from the quality kinetics and the D values and some of the related data, remember that the nutrients are relatively more heat stable compared to the microorganisms. So, if you can raise the temperature quickly, you kill the microorganisms quickly without much contribution of damage to the say the nutrients. So, if you look at here, this is the spore destruction. This happens at 140, much shorter time, whereas this is the quality kinetics, where you can be able to retain the product quality. If you look at here, much more retention of the quality is retained. Whereas at 121 Celsius, which is the traditional canning temperature, you are going to have almost a similar destruction of both nutrients and the spore forming bacteria. So, the concept behind the aseptic processing, can we raise the temperature very quickly to a higher temperature, 130, 140 Celsius, so that you can destroy the microorganisms without damaging the nutrients and the quality attributes. And traditionally, in the case of canning, you take the product. For example, if you want to make a soup, you prepare a soup and then pour the soup inside a say can, seal the can, and then assemble a set of cans, put inside a canning equipment, and then you're going to operate, and then you process for 30 minutes, 60 minutes, and then take it out, cool it down, all those things. Whereas in the case of aseptic processing, it's not a batch process, it is a continuous process. You take the product, so you prepare a soup, then you are going to heat the soup in a heat exchanger. So, there are a number of heat exchangers I think probably you may be aware of. One of them, for example, is tubular heat exchanger, where you have pumping the soup through a central tube, and then you have outer tube where the heating medium can pass through, thereby heating your soup. Or you can have a scraped surface heat exchanger, where you have a similar mechanism, but also you have an agitator which mixes the soup as it's being heated. Then you are going to cool it down, and then you bring into an aseptic environment. You take the package. So, here it does not need metal package. You probably can have polymeric pouches, or you can even have a paperboard with some type of appropriate protection. So, you can use some of those type of thing, and then you can sterilize them using some chemical or other means. So, for example, hydrogen peroxide often used with some of the polymer sterilization. Then you are going to fill the soup inside your package, and then you are going to do that in a sterile environment, and then you seal it, and then your product is kind of ready. So, this way there are a number of benefits. In a traditional canning method, you have to store a lot of metal cans. The metal cans maybe need to transport it from somewhere from the canning factory or some other place, and then you need to find a place for storing all those things. Whereas in this case, your metal, you are not using metal, you are using pouches. So, those film stocks does not need to be pre-made. So, you can probably able to store them much more economically, and then when your product is pumping through a continuous way, you are going to increase the heat transfer. So, anytime, so simple example is, if you are boiling water in your kitchen, you just allow that to do that, it probably take a little bit longer. On the other hand, you kind of put a mixing spoon, or you put a spoon and mix it, it is going to boil quickly. So, in the same way, in the product, when you are heating, you are pumping through, you are going to moving through at a particular velocity. So, those mixing help to improve the heat transfer, thereby you can able to reduce the damage to the nutrients. So, that is the concept behind the aseptic processing. So, if you compare this is the traditional canning method, whereas if you look at here, this over here, you can probably have, this is a retard pouch, and then this is your HTSG, your aseptic. So, you are going to have much shorter come up time to reach the target temperature. So, if you look at here, you may be reaching 120 Celsius, whereas that temperature can be accomplished much quickly with this, and then you can do cool it, hold it, and then you can do cool it down. And so, this has a very short come up time. So, that's way you can able to achieve much better quality of the product. Now, what is the criteria for making the product safe? So, it is similar to canning. So, canning has been practiced since 200 years or 150 years. So, I think this lot has been established, particularly from 1900s. This lot of scientific data has been established. So, what we are doing here is we are adapting some of those knowledge, time, temperature, you have certain log reduction of your target bacteria. So, the target bacteria for thermal processing for sterilization is Clostridium botulinum, and then the target indicator organism or surrogate organism for sterilization is Clostridium sporogenes. So, we use the same concept, except you are going to use much higher temperatures. And so, if you compare here the criteria for returning versus aseptic processing, you can see that you can able to accomplish much faster time. However, if you look at the calculation for the process, how much, where is the cold spot, how do you achieve microbial kill and so on, canning is relatively simple. So, for example, if I have orange juice and you want to do the canning of orange juice, you put a thermocouple at 1/3 from the bottom of your can, and then you measure the temperature, and then you deliver certain process temperature and time, and then you achieve sterilization. On the other hand, if you have a ham, which is conduction heated product, you put the thermocouple at the geometric center, and then again you measure the temperature for a certain time, and so on and so forth. You can achieve that. So, these are all cold spots in during canning processes. When I say cold spot, this is the least treated portion in the canning process. In other words, if you have any microorganism in that cold spot, if they survive, it can give outbreak. So, you want to avoid that. So, this is relatively straightforward and people have done over many years. On the other hand, in the case of aseptic processing, especially when you have liquid and solid mixture, the process calculations can be much more complex. And if you have looking at the energy efficiency, canning is more energy intensive. Part of the reason is you take, for example, certain energy, create a steam, and then there may be steam loss along the way, and then you deliver in the canning equipment, and then that in turn heat your product, and so there's going to be a lot of wastage of steam. Whereas in the case of aseptic processing, that is much more energy efficient. So, that is again one of the attractions for this technology. And then you are going to have, this is another reason, if you look at why canning is still very popular or commonly used. If you look at the handling and labor, it is relatively high, but I think the people have the canning equipment, whereas the aseptic processing equipment, the labor cost is low, but the equipment investment is high. So, it is kind of, you have to make a business decision. Do I invest large amount of money for the equipment and then followed by less money on the labor cost, or do I just use what I have and then try to work with what I have. So, there is kind of a lot of trade-offs. So, when you look at some of the technologies, you have one side the scientific decisions, the second part is the business decisions. Sometimes these are not very straightforward. So, there are complex things can interact with each other. So, what is the aseptic processing, how the equipment layout looks like? So, you have a product tank and then you have a pump. So, this is the pump here, and then you are going to pump this through a preheater followed by final heater. So, let us suppose I have some tomato soup and I kind of take that and then pumping it, and then you are going to preheat. So, when I say preheat, you may take the product, the soup may be initially at 25 degrees Celsius, then I am going to preheat maybe 70 Celsius. So that you kind of not expose the product to very high temperature immediately, whereas in the second heater I may be preheating to 140 C. So that the heating occurs a little bit gradually rather than just immediately, because there are products which may be heat sensitive or heat shocked. So, you kind of want to avoid that. Then you have a holding tube. So, remember we talked about placing a thermocouple in the geometric center or 1/3 from the bottom and measure the temperature and see whether the product reached the proper temperature, so that you have indication of sterility. That function is done here in the holding tube. In other words, what happens is if you have a product with the liquid and solid, you are going to pump through a holding tube. Holding tube is nothing but a simple stainless steel tube where the product is flowing through, and it may not be even insulated, but while doing here it has a certain length. So, from the entrance to the exit, it takes certain residence time. So, in other words, if you have a 5-meter tube and you are flowing at a certain velocity, it may take 30 seconds. Maybe if you increase the tube length to 10 meters, the velocity and the holding time going to change, all those things. So, you want to look at how much time I want my product at this temperature for how much time. You kind of have a calculation for whole tube. Based on that, you decide the length of the whole tube. So, this is kind of assure the sterility of the product in the aseptic processing system. Then it comes to the pre-cooling system, final cooler, and then you are going to aseptically package the product under those conditions. So, this is kind of very overall schematic of the aseptic processing system. If you later on we will talk about microwave heating, what you will see that the concept looks very similar. You are going to have a raw material tank, you are going to have your holding tube, your cooling heat exchangers, and then aseptic filler. The difference is this heater is replaced. This is a more traditional tubular heat exchanger or scrape surface heat exchanger. In the case of microwave, you may be using a microwave heater. In the case of heating, you are using a heater. So, the concept for aseptic processing can be adapted to ohmic or microwave, and then you can be able to achieve products same. Later on, when we talk about pulse electric field processing and high pressure processing, there are continuous methods which also employ very similar approach, but they also use similar type of concept, where this section is replaced by appropriate heat exchanging unit, and then you are able to achieve the process. Now, I think we are going to go through some of the components of the aseptic processing system. The first is a blending vessel. So, you may have soup. So, you kind of want to hydrate all the starches or whatever material, and then you can able to blend them, bring them at the same uniform temperature. And then you are going to have a timing pump which control the product pumping at a constant rate. So, what that means is, if you look at this pump here, normally what they use is a positive displacement pump. So, if you are studying food processing, you probably might have heard about pumps. There are two broad classification of pump. One is a centrifugal pump, another is a positive displacement pump. Centrifugal pump are inexpensive. They deliver the product by centrifugal force, but they can have a variable flow rate. So, in that means maybe 1 minute it may be delivering 3 gallons per minute. In second time it may be deliver 6 gallons or 5 gallons per minute. So, flow rate is unpredictable. The positive displacement pump, something like here, they are going to be much more expensive, but they are going to have a precise temperature control or precise flow control. So, if I set my flow rate as 3 gallons per minute, it is going to deliver consistently 3 gallons per minute. Why we are using a positive displacement pump? Because of this holding tube. Because in the holding tube, you want your particles spend the same amount of time. So, in other words, if I target residence time is 30 seconds, we expect all the particles, all the fluid in the system going through that 30 seconds processing time. If I have a variable pump, then the flow rate may be vary. So, in one time it may be 30 seconds, another time it may be 60 seconds, another time it is 20 seconds. That can put your food safety risk. So, here you are kind of trying to keep the consistency. That is where the positive displacement pump is kind of used, and they call that as a timing pump, metering pump, and there are different varieties of pumps are available. And you can use the centrifugal pump as a positive pump when you add what they call VFC, variable frequency drive. So, this control the variability within the pump and then make it consistent. So, instead of if you are going to have 3 to 6 gallons per minute flow rate change, then VFA drive kind of modulate that and then try to consistently deliver some constant flow rate. Now, there are different heat exchangers available. One is the direct steam infusion steam or steam infusion, plate heat exchangers, tubular heat exchangers, scrape surface, ohmic heating, microwave. If you look at plate heat exchanger, this is more commonly used when you do pasteurization of milk. Here the plates kind of held tightly together, you have a very light fluid passing through. So, this is kind of where that particular heat exchange used. In the case of aseptic, you may be using particles like liquid and solids particles. So, normally we do not use this heat exchanger here. Typically you may be using tubular heat exchanger. So, basically you have a tube, you have product is going through your food product, and then you are going to have what I call the heating medium going in the outside. So, this is your heating medium. So, thereby as the product moving through the heat exchanger, it is going to heat. The scrape surface heat exchanger is going to be similar, but inside here you are going to add another rod, and that rod has some type of scraping blade. So, that when the fluid is passing through, this rod is going to rotate, it is going to rotate at certain RPM, and it is going to scrape the surface, interior surface of your heat exchanger. Why we are doing that? So, for example, when you process protein products like maybe starches and so on, when you are heating them, the material can deposit and they kind of form what they call biofilm or something along those lines, and they can reduce the heat transfer efficiency. So, to facilitate removing some of those things and also facilitate mixing, you normally use the this rotating mechanism. We will talk about ohmic heating, microwave heating in the next 2 lectures. So, steam infusion, basically you kind of have a product here, and then you have a steam, and then you are going to mix them in this zone, and then you have a product. So, steam has a very high latent heat. So, when it mixes with the product, it is going to instantly increase the temperature of the product, and then you have heated product comes out. One of the limitation of this approach is steam essentially water. So, let us say you have a soup with a certain consistency, you are adding steam, essentially you are adding more water to it. So, you are going to dilute that soup, and unless you recover that steam added later by flashing, it may kind of alter the quality characteristics of the product. Steam infusion is another version. Here you have product coming in, and then it is going to spray it here, and then this chamber has a steam, and thereby you are going to be able to heat. So, it is kind of have those two. So, these steam infusions, infusion as well as injection usually associated with a flash cooler, so that any additional water you added during the treatment could potentially removed. Whole tube. So, at the heart of the aseptic processing is the whole tube, because this is the place where you determine or demonstrate the lethality of your product. So, it does not matter how much time the product spent in the heat exchanger, you do not consider the lethal effect, only when the time it spent in the holding tube. So, 30 seconds, 50 seconds, whatever that based on your thing, it is going to consider that. And then generally they are going to be slope upward 0.25 inch per feet, so that you can remove any potential air packet. And normally you monitor the temperature of the product at the inlet and the exit of the whole tube, and in the holding tube you are inactivating various microorganisms, bacteria, you may hydrolysis of starch and other things may happen, you may have caramelization of sugar, all those things may happen. Now, I talked about the aseptic processing temperature is 140, 130 Celsius. If you remember, water becomes steam, it boils at 100 Celsius. whereas your product here being processed at 130 or 140 C. So, how do I maintain the product in the liquid stage in my holding tube? So, this is where a back pressure valve comes in. So, back pressure valve essentially you add some additional pressure to the whole tube, so that it increases the pressure within the tube. When you increase that, you are going to, your liquid remains a liquid, but at a higher temperature. It may be at 130, 140 Celsius, but it flows as a liquid. If you don't have the whole your back pressure valve, it's going to start flashing or becoming like a steam, and that can create a lot of problems. Other thing is, when you have a continuous flow processing methods, a lot of times when you formulate things, you may have air get into your product, and it's okay to have air in other circumstances, but in the process operation you don't want to have air, because air is a poor conductor of heat. So, that means your product may not uniformly heat. So, you want to add a deaerator to remove the air. The other thing is, air also have oxygen. Oxygen, when you do store the product for a longer time, it can affect the shelf life and quality of the product. So, you kind of add a deaerator so that you can remove the air, and it helps to reduce the fouling, and it can help to reduce the volatile loss, reduce the foaming, and then you can able to maintain consistent holding time under those conditions. Then once you process it, then you can able to dump all the processed product in a such tank. So, normally, you may be thinking, what is the capacity of such tank? You may be thinking 50 gallons or 100 gallons, but you may have 100 gallons to thousands of gallons capacity such tanks. So, these are humongous tanks, and so for example, you may be processing orange juice, you are getting fresh orange, and then you are processing orange juice using aseptic. You can probably process millions of pounds, and then you can store them in the such tank, and then you can bring them later to package them into small individual size containers. And then you are going to fill this in a consumer package in a clean in place type approach. So, clean in place, we will talk about cleaning and sanitation later on, but clean in place basically tells us your processed product is kind of packaged inside a pouch, and you want to that environment where that filling happens free from any bacteria. So, imagine you have a chamber, that chamber you are going to maybe pre-treating with UV or some other decontamination step, so that it is sterile environment, there are no bacteria around, so that when you fill in, there is no contamination, cross contamination could potentially happen. So, I mentioned such tanks. This is just an example of some of the high capacity such tanks you can able to use, and so it's in fact, I think you can probably, for example, I'm talking US example here, Brazil, which is kind of close to the Americas there, you can get lot of orange juice and maybe millions of gallons of orange juice processed, filled in maybe $1 million type tanks, and then you put them in a ship, and then you bring them back to somewhere in the US. So, for example, Florida, where you have a aseptic packaging line, you can able to package them in small consumer type package. So, this kind of brings some flexibility for processing and then packaging at a different time intervals. Now, this process is aseptic, so that means it's a more self stable, so you don't need to worry about product being spoiled as long as you maintain the sterility of this tank during processing. So, this is Professor Nelson. He was a professor in Purdue. So, he was the one championed aseptic processing over the years. Just want to acknowledge his contributions. So, aseptic packaging, basically this also gives much more flexibility. You can have consumer size package. So, for example, couple of fluid ounce packages as long as, or maybe as high as 8 million gallons of aseptic tank. So, you can have a wide range of packages are possible. Now, a lot of the restaurants may be buying soups and other processed product, and they don't want a consumer size package. So, for that oftentimes you can use like what they call bag in a box. So, you may have a 55-gallon drum filled with your juice or soup, whatever it is, and then it is delivered to the restaurant, where the restaurant going to take a small portions at a time, but they consume a lot of soup or products over the time. So, they can able to empty it much quicker, whereas in the home you probably not going to use it that much over time. So, that is where the consumer size packages are kind of come in. And this just some examples of the different products aseptically processed, and this is just to give you some of the different packaging equipments available, like including bag in a box, cups, pouches, and bulk storage, and so on. So, the aseptic processing brings much more flexibility to processor, so they can able to process in different scales. Now, coming to the food safety validation, you have to be much more complex in this case. So, when if from your lectures on food safety kinetics and food quality kinetics, we know the D value provides the decimal reduction time, and then the Z value is the temperature sensitivity of the bacteria. From knowing D value and Z value, you can calculate what they call F value. Now, that is very straightforward to calculate for the case of canning. In the case of aseptic, it is much more complex. So, this is where we have to use a mathematical modeling tool. So, first you need to know the D and Z value of your bacteria under the appropriate conditions. So, if you are processing at 140 C, you need to know what my D and Z at 140 C. Then you need to know the residence time distribution. So, in other words, within my whole tube, how much time it is going to distribute. So, give an example, let us go back here. Suppose I introduce 100 particles with the liquid in the whole tube, and I count at the end of the whole tube here. Is all the 100 particles going to come in the same time? It is not going to come. So, some may be heavier, some may be lighter. So, there is going to be a pattern over time which is going to collect. So, this we call that as the residence time distribution. So, for this we have to collect that residence time distribution in the case of aseptic processing calculation. We also need to know the heat transfer. So, what is the heat transfer happening from the heating medium to the liquid? What is the heat transfer taking from the liquid to your solid? Maybe you have some carrots, you have some potato or other meat products in your soup. So, what type of heat transfer taking place? Then use a mathematical model to kind of look at the estimated thermal processing time, and you also try to look at the damage to the quality, like what is the destruction of nutrients or texture, all those things. So, you may kind of want to study the quality degradation kinetics. Then you kind of establish the thermal process time. So, with all the mathematical model, so you have a soup product, and then it says you have to process 20 seconds at 140 C. So, this is given this information by a model, but US Food and Drug Administration do not accept the model as it is. They want a biological validation. So, you have to take an indicator microorganism, and then you perform this process under those conditions, and then demonstrate that you achieve desired log reduction under those conditions. So, let us say you achieve 8 log reduction during certain process conditions, then you have to kind of demonstrate whether or not you can able to achieve that desired log reduction using the biological indicator organisms. So, the thermal process conditions, first you need to look at the residence time, model lethality, and then we modeled it with the inoculate pack study, and then you have to use the statistical confidence level for fastest 1% particle. What that means is, when you are doing processing, which one of the particle is going to be appropriate particle for doing your microbial safety check. In your soup, you may have potato, you may have carrot, or number of different products. Each may have different heat transfer characteristics. So you need to find which one of the particles going to move the fastest. So in other words, if your potato is going to move fastest, you choose that. On the other hand, if your meat has a lighter weight and move faster, then you have to choose the meat. So whatever move faster, you have to choose. Why the significance of moving fastest in the holding tube? Because when a particle moving fastest in the holding tube, it's spending the least amount of time in my whole tube. Remember, the holding tube is the place where I am demonstrating the safety. So that means if I spend less time in the whole tube, you may have a microbe in that particle that can contaminate the entire batch. So you want to make sure that that particle is inactivated, with free from pathogens and so on and so forth. So that's where they're kind of able to look at the fastest moving particle with certain characteristics. So here we are getting into a little bit food engineering or chemical engineering concept, the residence time distribution. Basically, the concept is, I mentioned here, you say inject 100 particles, you are passing through a holding tube, and then you are going to measure how many particles you are going to come through. Ideally, if all the particles, they may come in the same time, this is almost not practical. This is more practical. So initially, you may certain particles going to come through. This may take even longer. So from a processing part, particles are much more difficult to treatment. Whereas I'm concerned about, because this particle is spending less amount of time in my, so that my processing is done properly, so that this is treated. And then I have to do this under normal. In other words, if the industry is going to do at 5, these experiments need to be performed at 5 gallons per minute with 10 ml per minute, and then try to scale it up to conditions. Then once you have that, you also need to know the whole tube length. What is the minimum processing time you need, and then what is the velocity at which it's flowing through. Here we also need to know the fluid characteristics. So honey and some of these products, these are called Newtonian fluids. So what that means is, if you plot, have a straight line. On the other hand, lot of the starches, lot of the protein and other type of products are shear thinning. So that means with increasing processing time, they reduce the shear stress, thickening. So for example, if you have certain what I call, it's much thicker with increasing processing, so it becomes a shear thickening. So for that model, which I'm not going to go into details, but just to take here, you kind of have velocity based on 2 times the average velocity for Newtonian fluid or relationship. So there's a lot of math goes behind here. For the purpose of this class, I think there's a lot of books available where you can get into the details. The residence time, heat exchangers and so on. So, you have to consider some of those things, and to also consider is the Reynolds number. The Reynolds number kind of indicates what is the characteristic, and that is measured by this equation. Rho is the density, mu is the viscosity, and then you can able to see laminar. When it is a laminar, it is going to have this characteristic parabolic. While dilatant, it may have different characteristics. So, equations as well. Again, from a velocity, you calculate volumetric flow rate, and you also need to look at some of these Reynolds numbers. You have these things. Once you know your volumetric rate, you calculate the average velocity. From the average velocity, you times the average velocity, and then from there you also calculate your processing time, and from here you can able to calculate the holding tube length is the maximum velocity, which comes. So, this is kind of what you do. So, at the heart of the safety of your aseptic processing on your product characteristics and the microbiological safety criteria, you kind of size the whole tube. You have delivered the appropriate processes. I know, like, I think I am going through a lot of new information for some of you. If you can ask discussion. Then you also know the modeling. Those of you with the engineering background probably familiar. Again, depending on the sophistication, it can be one dimensional or three dimensional. The heat transfer input to the liquid and the solid, and then how and so on, and then they utilize different properties, and then the mathematical model help the processor to. I had 5 gallons per minute, how do I process my samples? What if I increase the temperature from this? How do I product characteristics look like? So, there are a lot of those what if scenarios can happen, whereas to show you are have a safe product, they expect biological validation. So, in a demonstrate the safety, and then it has to be something relevant. So, is often used because that is very similar characteristics as Clostridium botulinum, and then it can grow and spoil or cause outbreak in the process. Aseptic processing is a continuous processing method, still it is. So, your temperature and time is the principal critical process. To demonstrate the safety, you need to have certain temperature. So, that is the principle behind it, but you also you are using tubular heat exchanger, you are using Omi heater, all those things can alter. Now, in terms of texture and viscosity, aseptic processing had a minimal impact on. Out a little bit softer than fresh, but much better than the canned product, and but generally the meat purees are not substantially affected by flavor. The product is much flavorful, and you, for example, in soups, things like that, you retain the natural flavor. You are doing high temperature short time, so that means it's going to better retain the nutrient, and then most of the vitamins and other things are remain unaffected. Reference material. So I think so. This book probably one of the very, and this is guidelines from FDA. So you can probably, if you want to learn. Now we can stop and ask any questions.
Good morning. The critical parameters monitor retorting cycle.
Critical process parameter, retorting cycle, temperature.
And what if any cold spot is means in the sum of the batch, if any cold spot remains?
So basically, you are monitoring time and temperature at the cold spot. So for example, if you are processing spam, it's a conduction heated product, you are monitoring at the geometric center of the can the time and temperature, so make sure that it reaches the sufficient temperature under those conditions. Okay. Time and temperature are in the case of aseptic, yes, it's also the critical control, right. So how do you monitor? I think it's different. So in the case of canning, you're going to take the product, actual product, and then put a thermocouples and measure it. Whereas in the case of aseptic, the liquid and solid are flowing. So you cannot put a thermocouple and chase the thermocouple in the holding tube. So you basically put thermocouples at the entrance exit in the whole tube, but you predict the temperature distribution within the liquid and solid using mathematical models. So it's kind of little, instead of physical measurements, use the mathematics to predict your temperature values.